Hello, and welcome to my CS3 final project. For this project, I decided to create a rocket engine calculator, which takes a list of inputs and creates a bunch of outputs based on the given inputs. I decided to do a different route from what was available online. Online, there is a bunch of NASA calculators for calculating these statistics based off gamma, pressure, temperature, but I couldn't find any that uses the shape of the engine and then the fuel to calculate them. So what I did, I used these statistics, engine length, fuel pressure, combustion chamber length, combustion chamber diameter, nozzle throat diameter, exit nozzle diameter, the fuels, and then pressure, exit velocity, and temperature. And then that calculates different. Enter something. So we have 15, 150 psi, 10 chamber length, 6 diameter, 3 nozzle diameter, and 8. So this is the total length. Enter starting fuel pressure. This is the combustion chamber, so where like the initial pressure is built. This is the diameter of that chamber. The nozzle where it gets compressed, and then the exit which is accelerated by like some physics effect. And we'll do pressure and do like nitrous oxide, and we'll color the engine in the next part based off pressure. So this created a window, additional window that gives us stats for each, as well as the stats down here. So we can see this engine looks kind of like this, has about a pretty shorter. It's not really accurate in like the zoom length, but shorter than others. The sizes here, and it creates like 5,000 pounds of thrust, 315 pressure. It's pretty hot and pretty medium speed exit. And it's a stable engine. The colors are the stability. So if I can increase it by 1,500, it'd be unstable. And that's why you get the red engine and it's wonky shaped exhaust because it would have exploded by then. You can also, another cool feature of this project is you can create multiple windows so you can compare different engines. Like if we put this in the middle at 500 psi, you can get a engine that's closer to the limit and compare the statistics of all three. Like the temperatures, like this is 10 times hotter. This is in the middle here. This pressure is less than this one, but greater than this one. You can compare all three. You also have the option of lots of fuels, including ones that can make explosives, and you can color it based on X velocity or temperature. So we'll do we'll do this one again with X velocity, and it has a normal X velocity, so it won't be pushing back too hard and creating like much torque. And you can compare the exit plumes in each one and show the different shapes. That's mainly it for the code. Or for the demonstration. Another cool thing I have on this is I made a jar file out of it, which is on my desktop, so you can just run this program. And it can be completely separate. You don't actually need the files here. You can just run this separately. And that was one of my new things. I learned how to do a jar file, which is done through creating a manifest like this with the icon picture, the name, and then using some terminal commands here to write, like have these classes, and then have the jar object be like have those attributes as well and be able to work with that. So I learned that on the internet and able to apply that. And the other new element of this is I also did some Python, some more swing stuff in Java, and did some more advanced math. So I'm going to walk through my code now. We start off with a bunch of imports, and we get to this part I added recently. It adds like the icon image, and it sets it for when you run it up here, says this one, and then sets down here, and also allows it to be tracked by the manifest. And then we get to here, we get the inputs panels, split a few of them, and then we get the fuel box. There's a lot of fuels. There's like the Jet A, pure alcohol, ammonia, those are like the fun ones. You have like normal ones like RP1, hydrogen, methane, ethanol, and then some more exotic ones like right here. Then you have the fuel box, and you have oxidizers, standard oxidizers, a few fun ones like these two, which are pretty explosive. And then you have the last box, which is the type of coloring you want on your engine. Then we go to the outputs. This is for the bottom part of the panel. So when we run it, there's like down here. That's what these are. We start the J panel, and then we calculate statistics, which is the fun part of this. So for this, we do a lot of math. So this makes sure everything is valid in a certain format, and tells you what's wrong, it's not. Okay, engine coefficient. I'm not going to explain what it is. It's just a bunch of diameters and stuff to get a coefficient that can be used later on. This is our thrust. Uses the standard thrust ratio from NASA. A bit modified to work with this here, and the fuel pressure factor. So it's slightly different and do some different new math for that, but that was fun. This is very standard way to calculate specific pressure. It's not the most accurate. There's a bit of give because I use this constant here into the calculating the ISP constant myself, but it's close enough where it's not going to matter that much. Pressure is super simple. You can use pivot for that. Then here is where we set the pressure coefficients or the fuel coefficients. So each fuel has its own coefficient, which it's like you find online. And these coefficients kind of measure a bunch of different factors and are used for when you're multiplying a fuel with as a fuel factor. Then you have the pressure ratio, which is different from pressure, and it's the ratio of like the chamber to the throat. Calculate temperature, super simple. Pivot again for that. Exit velocity, this is a bit weird. I had to do some general estimation by using a constant for turbulence to get it anywhere near accurate, because I didn't want to calculate the turbulence of the engine and like the wake. So this is like 80-90% accurate. So there's some errors at like super high speeds, which when the engine's about to explode. So, but this is mostly accurate. Okay, and then we go to additional window, which is created each time you make a new engine. Like when they press calculate, it'll create another window here. And then for this, I use a bunch of paint components, and I do a bunch of centering and stuff to get this to look like. This is for the combustion chamber. This is for the converging section. This is for the diverging section. And this is for the exhaust, which was super annoying to code because it kept doing weird stuff and not being centered. This sets the same thing as the last one. It sets the those outputs on so you can compare your engine together. Labels. Okay, and this is the engine color stuff. It's pretty rudimentary. If your engine is above 3,000, most of the metal, which is aluminum in this case, I'm designing the engine. All the engines are hypothetical would be out of would easily break at 3,000 and not survive. Same at 5,000 temperature, or 5,000 temperature and 5,000 exit velocity. So those are just rough estimates. They could be more accurate, but I don't. It takes a lot of more math to do that, and this is pretty close. So if your engine's red, not going to work in real life. Okay. And now